introduce our speaker, who is here with us, but just to be reliable, we're gonna first attempt to play his video. The speaker is Carlos Enrique Medeiros de Saboia. He is a civil engineer and holds a master's degree in optimization with focus in large-scale combinatorial optimization from the Computing and Systems Engineering program at the Federal University of Rio de Janeiro. Since 2002, he has been with CEPEL, which is the Brazilian Electric Energy Research Center in Rio de Janeiro, and he works on mathematical programming projects with applications in energy systems. So he will talk today about hourly pricing and day-ahead dispatch setting in Brazil with the DESSEM model. And now I will attempt to play his video. And now I will share the screen. Can someone confirm that they see the presentation of Carlos on the screen?
Yeah, we can see it.
I can see.
It's not playing the audio, Anton.
Sorry, audio also.
It's not playing the audio.
It's not playing the audio.
No, when you're sharing your screen, when you're selecting your screen you want to share, you have an option at the bottom to enable to share the computer's sound.
Share computer sound, got it. And try
If you check that, it should work.
I am from CEPEL, the Brazilian Electric Energy Research
Yes. So good.
Center in Rio de Janeiro, and I'm going to present the paper Hourly Pricing and Day-Ahead Dispatch Setting in Brazil, the DESSEM model. In Brazil, since 2000, the weekly hydrothermal dispatch has been centrally coordinated by ISO with the optimization tools NewWave and DECOMP developed by CEPEL, based on dual dynamic program. And the market price are setting by the market operation in weekly time steps. The model DESSEM has been developed by CEPEL since 2000, and in 2017 has begun its validation process to provide the optimal hydrothermal dispatch for the day ahead in half-an-hour time steps and the hourly market prices. In this work, we present the main features of this model and the practical aspects, such as the solution approach that made possible its official use by the Brazilian ISO since January 2020. Here we can see the Brazilian generation mix that shows the hydro-dominated characteristic of Brazil. Actually, the hydropower plants still keep responding for around of 70% of the total installed capacity. And we can see also an increasing participation of intermittent sources. Brazil has a large-scale system, predominantly hydro with stochastic inflows to reservoirs and long distance between generation source and load. In this figure, we can realize that operate the system is as complex as to operate the whole European electric system. In this diagram, we can see the total amount of hydropower plants throughout the whole country, coupled in cascade that are centrally dispatched by the Brazilian ISO. The chain of optimization and simulation models developed by CEPEL and validated by the government institution and most of private electric companies is officially used in the hydrothermal power generation plan of Brazil. to dispatch the system and set market price, among others government planning activities. In the central structure of this chain of models are the model New Wave, devoted to long-term operation planning, use stochastic dual dynamic program. The model DECOMP, devoted to medium-term operation planning, use deterministic Bender decomposition. And the model DESSEM, devoted to operate the electric system in early days, that employs branch and cut together with specific feasibility pump and local branch approaches. These three main models work in an integrated form. The New Wave is run at the beginning of each month to build a cost-to-go function to model the comp that is run at each week and also builds a cost-to-go function to model the same. This last one is running at each day to provide the early dispatch and spot price. This time continuous framework among these models we call the Rolling Horizon application. The main objective of the hydrothermal coordination problem solved by DESSEM is to minimize the thermal generation cost and the water value in the reservoirs coming from the cost-to-go function from model DECOMP. The model takes into account a detailed model of hydropower plants in Cascade, the modeling of thermal power plants considering unit committed aspects, the intermittent generation technologies like wind and solar power inside a DC flow network in an early time step. The cost information of thermal power plants comes explicitly from the generation cost and the startup and shutdown cost as well. For hydropower plants, it comes from the water value, that is a function of the reservoir's volumes and the efficiency of the hydro plants available at each point of operation. Finally, the intermittent technologies like wind have no generation cost, and the model can decide to use it as long as allowed by the daily wind forecast. The DESSEM model considers the power balance in each system area, that is a set of electric buses, and represent the main electric regions of Brazil. The generation technologies are plugged in each specific bus that are linked together through electric lines. In the Brazilian ISO operation, it considers the first day in a half an hour time step and the following days in aggregated hours time steps that are coupled with the cost-to-go function come from the comp at the end of the week. In model DESSEM, the efficiency of a hydropower plant is a function of the water head. That is also a nonlinear function of turbine and spilled water. The so-called hydroproduction function is therefore considered through a piecewise linear approximation in 4 dimensions. The operation of the coupled hydropower plants is modeling in a detailed form that includes pump stations, filling of dead volumes, channels between reservoirs, modeling of river sections, evaporation in reservoirs, multiple uses of water, fluid control constraints, among others. Due to the time steps in periods of hours, the water volume discharged in a hydropower plant may not be available in the subsequent plant in the next period, since in some cascades, the water can spend days traveling. In the model, the river routing is modeled use water propagation curves between reservoirs, and that introduce in the model a more complex coupling, because a plant can be coupled with its subsequent one in several periods of time. The thermal unit committed modeling employs classical constraints such as minimal generation, minimal up and down times, startup and shutdown costs, and ramping constraints. It also considers the startup trajectory from the null to minimal generation value, as well as the shutdown trajectories between the minimal generation to the null value. The operation of cycle combined thermal power plants was considered through the concept of configuration modes. Each unit physically represents an integrated operation among real units of gas and steam turbines. This detailed representation is important since there is, in Brazil, thermal combined plants with high capacity around of 1.5 gigawatts. Finally, it was modeled the possibility of transitions between units. In the following example, after a unit representing a gas turbine reaches its minimum, there is a transition to a unit representing a combined operation between gas and steam, without the need to first follow the shutdown trajectory of the first one. This model was based in an approach from literature, but some new concepts was considered and modeled with the use of binary control variables. The GC network is considered without explicitly represents the phase angles in the model. After optimize the problem, the injections are applied in the corresponding buses to solve the DC flow that gives us the electric flow in the lines. If any line is violated, a new constraint is included and the model is run again, until no more violations in line limits being found. Into this concept, the model considers line flow limits constraints, ramp constraints on line flows, and power transmission losses. It also considers security constraints on the combination of flows in some lines that are given by the merely statewise concave function, in which we can employ a lower piecewise linear concave approximation of it, or given by tables. Here we present the overall formulation of the corresponding mixed integer linear program with constraints such as electric load, electric network, water balance, approximated hydro production function, operative constraints, thermal unit commitment. The problem is a large-scale mixed integer linear program in which a typical daily instance used by the ISO has approximately 100,000 binary variables, 500,000 of continuous ones, and 500,000 of constraints. Also, the number of constraints grows along the iterations, since the network constraints are not binary. They are included on demand when violated. To solve this problem efficiently, it was developed an approach that's used in an integrated form the interior point algorithm for linear program, the branch and cut algorithm mixed integer program uses the simplex solver, and a modified version of feasibility pump. To solve this problem, we have tried some approaches ranging from exact to approximate ones. In the exact approach, we solve to optimality a sequence of mixed integer programs to introduce violated network constraints. Due to this reason, the computational time becomes around of 12 hours. That is forbidden for the application of ISO to determine the daily Brazilian hydrothermal dispatch. In the approximation approach, we found a feasible integer solution inside an optimality gap. First, we use the linear relaxation in the iterative approach to introduce violated network constraints, finding a lower limit. In the sequence, we solve a mixed integer program and fix the optimal thermal unit commitment status in order to find an upper limit after applying the iterative network approach again. With the approximation approach, the sequence of linear programs followed by a single mixed integer program drastically reduces the computational burden. However, in the set of approximately 250 instances of shadow operation from January to October of the last year, an specific amount of cases present the computational solution time ranging from 2 to 4 hours. Unfortunately, the solution time was still not adequate to use the model by ISO inside the daily framework to operate the Brazilian system. Therefore, the ISO imposed that the maximum allowed time in most of cases must be 2 hours. We have developed a modified version of feasibility pump to model DESSEM that can be briefly summarized as follows. 1. Works with the linear relaxation solved with interior point method. 2. Rounds the fractional unit commitment status to the near integer. 3. Adds a penalized term in the objective function inducing the convergence to the desired integer. 4. After some feasibility pump iterations, for alternate units, fix those whose status are still defined. In the approximate final approach, we use the modified feasibility pump to warm start the branch and cut with a partial fixed unit commitment status, thus reducing the computational complexity. With this new approach, we have attained the condition imposed by the ISO relating to the computational time. In the set of instances of the shadow operation from January to October of the last year, the average solution time was 50 minutes, and only 5% of the cases were solved in more than 2 hours. Also, in the whole set of official instances of this year, the average solution times was 34 minutes. Since the DESSEM model is a non-convex problem due to the binary unit commitment status, we have used the approach of UNIL that fixes the optimal commitment and solves the resulting linear program, thus obtaining the respective Lagrange multipliers. The market price of system areas are given by the weighted average of the nodal price in all buses. Finally, we have a summary of the validation process started in 2017 to officially use DESSEM to provide the optimal hydrothermal with dispatch for the day ahead in a half an hour, time steps, and the early market prices. This last one is still under discussion, and it is expected that the early price being adopted in Brazil at the beginning of 2021. Now follow the references. Thank you for your attention. Obrigado.
Excellent. Thank you, Carlos, for that. So I invite questions. We have a couple more minutes remaining. I'm not sure if you can still hear me, or I need to.
Yes, we can.
Excellent. So, question by Alexander Street. How is the word now is to you. So, how is the renewable variability, and in particular, how is the renewable variability and uncertainty considered? Are there reserves being co-optimized? First question.
Okay, the renewable variability, the renewable fonts, we are considering the forecast from ISO. At each day, we have the forecast for the next day, and this one, the DESSEM optimized without generate cost. Né? And about the second question, do you consider the cost? Do you consider the cost of the cost growth function, cost in the gap assessment when testing the convergence? The gap assessment? No, in the cost to go function of the we consider just the cost to go function from the comp, and the convergence is about the mixed integer problem by the branch and cut. By concern here is the water cost will not be too large when compared to the daily cost. Sorry, Alexandre, could you repeat the second question?
Yeah.
Please.
So what I think Alexander means is that if you have a target gap of 1% and the cost to go function is huge value, that 1% has very different meaning than if the cost to go function is a small value. because it's 1% of a big number versus 1% of a small number. So I think his question is when you are, you understand?
Okay.
Yeah.
Yes, no, I understand now. The cost to go function, it comes from the middle model, the decomp, and we have found in all of the cases, in 250 cases of the last year, almost the null gap. You know, I think there's a good results, and yes, I think this.
It's a yes/no question, though. So, do you consider the cost to go function in the gap?
We consider fixed cost to go function, you know, coming from the middle term model, and this cost to go function goes to the mixed integer program, and then branch and cut and the feasibility pump optimize the problem until the null gap. Just that.
Okay.
You know.
All right, cool. I think we should, thank you very much, Carlos. I think we should proceed to our next